So you may be familiar with the traveling salesman problem. The traveling salesman problem is a problem that deals with finding short routes that visit a number of locations. The traveling salesman problem is a famous example of an NP-complete problem. In a very simplifying definition, if you were to classify problems as easy or hard, NP-complete problems are the problems that are hard. So when we look at them, we're interested in figuring out which characteristics make these problems hard to solve so that we can better be able to deal with them. So in the research we did, we looked at a number of grid logic puzzles published by the Japanese puzzle company Berkeley. So I have 4 examples of the puzzles here. All of these puzzles have been proven to be NP-complete. Puzzles are actually very natural candidates for NP-completeness research because of 2 characteristics of puzzle design. One of the characteristics is that when designing a puzzle, you wanted to have a small number of rules so that it's easy for people to understand the puzzle. So for instance, the rules of Sudoku could be explained in a single sentence, where it's put the numbers 1 through 9 exactly once in each row, column, and box. When you have a simple set of rules, it makes it easier to isolate individual constraints of the problem to see how they affect the complexity. But then the other characteristic is that you'd like the puzzles to be challenging to solve. So in general, these puzzles do turn out to be NP-complete problems. So in this way, studying these, it's useful to see how different constraints of the puzzles affect their complexity. So for my project, I looked at a puzzle called 5 cells. On the left is an example 5 cells puzzle, and on the right is the solution to that puzzle. There are 2 rules of 5 cells. The first is that you have to divide the grid into shapes that are 5 squares large. So you can see these shapes on the right. The second rule concerns the numbers in the grid. You define heavy borders as the edge of the grid or the borders between the polyominoes. A number tells you how many heavy borders are adjacent to it. So if you look at a 3 clue, for instance, 3 of the 4 borders around it are heavy borders. So my strategy for proving that 5 cells is an NP-complete problem is called a reduction. You can essentially think of a reduction as a conversion between a problem, a conversion between problems. I'll talk more about how this reduction works in a little bit. But the problem I'm reducing from is called 1 in 3 graph orientation. This is a graph theory problem. I've put an unsolved instance of the problem here. So the problem is solved on a 3 regular graph, which means that every vertex of the graph connects to exactly 3 neighboring vertices. Now, there are 3 different kinds of vertices in this graph. The ones marked with circles are called literal nodes. These always come in pairs. And then you also have, you can see at the bottom, on the left is a clause node, and on the right is a negated clause node. When you solve the problem, your goal is to figure out the orientation of every edge in the graph. So here I use arrows to mark the orientations. For every one of the literal nodes, the edges connecting to it all must point in the same direction, either all towards the node or all away from the node. For the clause node on the left, exactly 1 edge has to point towards the clause node. For the negated clause node on the right, exactly 1 edge has to point away from the clause node. So you can look at this visual and verify that all of the nodes are satisfied correctly. So this problem, I'll abbreviate it 1 in 3 GO for 1 in 3 graph orientation, has been proven to be an NP-complete problem. So the general strategy for this proof is to try to implement a 1 in 3 GO problem as a 5 cells puzzle. So every aspect of the 1 in 3 GO problem will have an equivalent 5 cells puzzle that goes with it. You can put these 5 cells puzzles together to form a large 5 cells puzzle that is capable of representing any 1 in 3 GO problem. Now, in order to solve the 5 cells puzzle, you would have to solve the 1 in 3 GO problem as well. And because we know that 1 in 3 GO is NP-complete, with a few other details, that allows you to conclude that 5 cells is NP-complete as well. So the individual pieces of the puzzle I'll be making are called gadgets. I need a gadget that's capable of representing the empty space between the other gadgets. I need a way of representing a wire that can point in either of 2 directions. I need a gadget that allows a wire to turn. I need a gadget that allows 2 wires to cross over each other without interfering. I need a gadget that's capable of representing 2 adjacent literal nodes. Remember that these always come in pairs. And I need a gadget that represents both the clause node and its corresponding negated clause node. Every clause node will have a corresponding negated node. So first, here's the empty space. It's a tessellation of X-shaped pentominoes. Pentominoes are 5 square shapes. Each 0 clue here determines a single pentomino. Now the wire is put in the empty space between these pentominoes. The wire has 2 possible orientations, and they're pictured here. The wire on the left is pointed towards the left, and the wire on the right is pointed towards the right. And throughout this presentation, I'll use colors to show the 2 different orientations of wires in the gadgets. So here's the turn gadget. You can see that the edges of this gadget connect to the right side and the bottom side. So this would allow a wire to turn. Now, I'll give a brief talk about why this gadget works. If you look at this highlighted 2 clue, it already has 2 heavy borders next to it, so it has to connect to the other 2 cells adjacent to it. Now, the 2 clue that's highlighted now, it's either connected to the 4 cells we've already identified or not connected. If it is connected, we end up running into a problem. There's no way to satisfy the 3 clue at the bottom. It can have at most 2 heavy borders next to it. So the 2 clue above would have to not be connected to the ones already shown. The 4 cells connected at the top have to use a 5th cell to make a 5 square shape. It has to be one of the 2 highlighted squares remaining. So this is one option, and this is the other. These end up giving you the 2 possible orientations of the wire as it travels through the gadget. So in this way, this gadget would allow a wire to turn. So next is the crossover gadget. This allows 2 wires to cross without interfering with each other. This is one of the possible solutions to the crossover gadget. If you look at the colors of the wires and their orientations, you can see that orientation is maintained as the wire passes through the gadget. And this is true of both wires. This gadget has 4-way rotational symmetry. So this corresponds to wires pointing down and to the left. But by rotating this gadget, it would allow you to have all possible directions for the crossover. After that is the dual literal gadget. This gadget represents 2 literal nodes next to each other. A reminder that in a literal node, all of the edges have to point in the same direction. So this is one possible solution to the dual literal node in the 1 and 3 go problem, and then the corresponding gadget. Here, red shows that a wire is pointing away from the gadget, and blue shows that it's pointing towards. If you look at the correspondence between the letters, you can see how it lines up between the problems. And then here's the other possible solution. I won't give a proof, but these are the only 2 solutions to the gadget. So it would have to have one of these combinations. And then the dual clause gadget represents 2 clause nodes, the regular one and its corresponding negated clause node. Again, you can see the correspondence between the letters and the wires within the gadget. So here's one possible solution. If you look at the top part of the gadget, remember that the clause node has to have exactly 1 wire pointed inwards. Here, blue wires point inwards. You can see how exactly 1 connects. And then on the bottom, you can see how exactly 2 are pointing inwards for the blue. Here's one of the other possible cases. And then here's the third. A reminder that there's 1 wire pointing in on the top and 2 pointing in at the bottom. So as a whole, these gadgets we've designed allow us to implement any 1 and 3 go problem as a 5 cells puzzle. If we start with, I have on the left a piece of a 1 and 3 go problem, we can map it onto a square lattice. Then we rotate and scale this lattice to line up with the tessellation of X pentominoes, and then put the corresponding gadgets that line up with the problem. So in this way, you would get a puzzle that represents the 1 and 3 go instance. And the solution to this problem would correspond to the solution of the 1 and 3 go instance. So in order to solve the 5 cells, you would have to solve the 1 and 3 go problem that is NP-complete. So I am leaving out a few details, but from this, we can conclude that 5 cells is an NP-complete problem.